Good morning, students. Today, in this class, I will discuss something very enchanting, something which might appear completely unrelated but are deeply connected. The topic which you see on the board, it cites three important fields, subjects. One is the electricity, second one is the magnetism, and third one is the relativity. Now, relativity, I'm not here to discuss that, but I will use one of its law, which says laws of physics must remain the same in all the inertial frames. Inertial frames, we give this term to such frames of reference which are not accelerated. So with respect to Earth, for example, suppose if we assume Earth to be an inertial frame, then this board, this building can be supposed to be an inertial frame because it is not accelerated. Likewise, anything which is moving at a constant speed will be treated as inertial frame. Those things which will be accelerated relative to some inertial frame of reference which have some non-zero acceleration, such frames we will call as non-inertial frames. So these things are known to you, students. You have read them in standard 11th. As this statement which I have indicated in the box suggests that if you observe a particular phenomena in physics or law in physics from one inertial frame and somebody else observes it from his own inertial frame of reference, these two laws must produce same effect. If law of conservation of momentum is valid for me who is standing still at this place, it must be valid for a person who is moving with a constant velocity in any direction. But the moment he becomes accelerated, something else will happen. We are not going to discuss that. For all inertial frames, whatever speed a frame of reference has, irrespective of its speed, as long as its speed is not changing, velocity is not changing, or I can say as long as its acceleration is zero, we will have same laws of physics, irrespective of the point of observation or frame of reference. Now, why I discussed this in this context of electricity and magnetism? So I would try to explain my point with the help of one example. This activity you have already seen and enjoyed. So there is a copper coil hanging from this particular support, and we have some magnet. If I bring north pole of the magnet towards this coil, we have already discussed Lenz's law. According to Faraday's law, we know there is some current which is induced in this coil that produces its own magnetic field. There is interaction between the magnetic field produced by this coil and this magnet, and there is some interaction, some force, sometimes attractive, sometimes repulsive. You know that if I bring this magnet, suppose north pole, towards the coil, then the face of the coil towards this magnet also behaves like a north pole. And how do we know that? We can use Lenz's law or Faraday's law to find that. Similarly, if I take north pole of this magnet away from this coil, like so, then in that case, this face, this side, will behave as south pole, and the other face will behave as north pole. So there will be some current in this coil. Electrons will flow around this wire. That current will produce magnetic field. Between this magnetic field and the magnetic field produced by the magnet, we say there is some interaction that takes place that causes this particular effect. And because of that, when I bring this magnet close to this coil, it repels this one. And when I take it away, it attracts this one. So this is the case. And the coil starts oscillating. I would like to put some more insight into this discussion, and I'll try to bring in relativity in this context. My point is, if my frame of reference is the magnet, that means if I position myself on the magnet, I should observe something. And if I position myself on this coil, then also I should observe something. And both of them, because the magnet is also inertial frame, and this is also an inertial frame. It is at rest, we say relative to the board, say, or the room, and this magnet we are bringing. First of all, and we assume the magnet to move with constant velocity so that we can assume it safely to be an inertial frame. First of all, case 1, I will choose my frame of reference on the magnet. What does that mean? That means I would observe things assuming myself lying over that magnet. When that magnet moves, you position yourself on the magnet and then imagine what goes around you. So actually, I was moving this magnet towards the coil. But if you position yourself onto this magnet, you will feel as if the coil is moving towards you with the same velocity but in opposite direction. Let the speed of the magnet with which I bring it towards the coil be v, this one. V is the velocity of the magnet towards the coil. But since my frame of reference is on the magnet, I will feel as if the magnet is at rest. So I will assume this to be at rest. And I would feel instead that the coil is moving towards me with this velocity in opposite direction. Relativity. Now I would find that there is some current in this particular coil. What is the cause of that current? So force on charged particle, you know students, Lorentz force is given by the formula Q times E vector plus V vector cross B vector, where the terms have their usual meaning. You are positioned here. You feel as if this coil is moving towards you. So each and every point on this coil, in other words, each and every free electron on this coil has a velocity v towards right as per this figure. I consider two elements, one at the top, one at the bottom. Now, how is the coil placed? As you can see here, the coil is like so. Half of this coil comes out of the board, and the remaining half, which is shown by dashed curve, is inside the curve, inside the board. So the plane of the coil is perpendicular to the plane of the board. So board is like this, the coil will be like so, half part outside, half part inside. Magnetic field lines I have drawn for this particular magnet. So this person will feel, who is positioning himself on the magnet, that in this region of magnetic field, which I call as B, the free electrons of this coil are moving with velocity v. And therefore, according to this particular formula, there should be some force on those free electrons. Now, according to this person, there is no electric field, so I'll put this term 0. So according to him, the only force is Q times V vector cross B vector. Now, in this figure, V vector is towards right, and B vector is along the tangent to the direction of magnetic field. So at this point, at the top point, if I draw tangent to the magnetic field line, it will be like so. And this is V vector, as I have indicated here. So this is V vector, and this is B vector. Both velocity vector and magnetic field vector are in the plane of this board for this top element. So therefore, V cross B should be perpendicular to the plane containing these two vectors. You can find it easily. V cross B. It points along this thumb. That means it will point outside the board, coming out of the board. So I'll mark it with a dot. V cross B. So that electron will experience a force in this direction. So if we have this coil, this one, at the top of this coil, the free electrons will experience a force in that direction towards you. Let's see what happens at the bottom. At the bottom, if you draw the tangent to the magnetic field line, it will be like so. The velocity vector remains in same direction for all the electrons, free electrons. And now if you find V cross B, you see, this is V vector and this is B vector. So V cross B points into the board. So I'll represent it by cross. The force on this particular electron will be into the board. So what we discussed just now, is that the force on the electrons which are at the top, which are moving in that direction relative to the magnet, is towards you, and the force on electrons at the bottom is towards me or towards the board. Likewise, you can use right hand rule to find q v cross p direction at different points. You will find it will be along the tangent to the loop. At each point of the loop, circular loop, the direction of force will be along the tangent. And because of that force, the electrons will start moving in circular path around the circular loop, along the circular loop, in fact. So because of this force, electrons start moving along the loop. And when electrons start moving, there will be some current, and this we call as induced current. So this is the expression of Faraday's law on the basis of Lorentz force when seen from the magnet perspective. Now let us see what happens if we see the same thing from the perspective of the coil. Imagine yourself sitting at a point on the coil, on the wire. What would you observe? You see that yourself, the coil, is at rest and the magnet's north pole is coming towards you. So what you experience is a varying magnetic field. So in second case, the frame of reference I'll choose on the coil. Frame of reference is on the coil. So if you station yourself onto this coil, you will see that there is some magnet which is coming towards you. Because the magnet is coming towards the coil, the magnetic field will be found to be increasing. Similarly, if you take the magnet away, the value of magnetic field will decrease. So there will be some change in magnetic field. So in this frame of reference, the coil will be at rest. Coil will be at rest. And it will be subjected to changing magnetic field. Magnetic field will be changing because of motion of the magnet. Okay. Now imagine a free electron onto this coil. The Lorentz force on the free electron or charge q is given by F is q times v vector plus b vector, where v is the velocity of the charge, which according to our frame of reference is 0. V is not the velocity of the magnet. We know a charged particle would experience a magnetic force only as long as it is moving. This suggests this v cross b. If the velocity of the charged particle is 0, in other words, if a charged particle is at rest, I bring a very strong magnet in front of it. It will have no magnetic force on the charge. The moment charge starts flowing, then the term q times v cross b comes into existence and there will be some force. So this is very surprising that since I am considering my frame of reference on the coil, I will say that the electrons, free electrons or the charge carriers are at rest, and therefore by bringing the magnet closer or away, whatsoever it may be, whatever be the value of magnetic field, force, magnetic force, I should write it as magnetic force on each and every charge must be 0. And if the magnetic forces are 0, how come they will move? And if they don't move, how come there will be induced current? So I should conclude that there is no induced current. But if I do so, I will disobey this particular law, a very, very general law that all laws of physics must be same in different inertial frames. So where is the problem? The problem is somewhere here that goes unnoticed. The Lorentz force is given as q times E vector plus V cross B. This cannot be wrong. It has been tested. It had been tested. What I am discussing now has been thought of long back. It is just mere repetition of that. But still, I derive pleasure discussing these things. This cannot be wrong. This cannot be wrong. Because if you connect this to galvanometer, we will find there is some current. There is something wrong with our justification, which I discussed in part B. E plus V cross B is there. Let me remove this. B is also V cross B is 0 because V is 0. So this part I will make it 0. But the entire term should be non-zero. This is non-zero because if I have observed current in the first case, I must observe current in the second case. Laws of physics must remain the same. If this factor is non-zero and this term is zero, that is only one possibility. There is only one possibility that there must be electric field. And this helps you to think and propose that a changing magnetic field as observed by the person who is resting on the coil must produce electric field in the coil, in fact along the coil. A changing magnetic field must produce electric field. If there is some non-zero force, that cannot be because of magnetic field, because the charges are at rest according to that person. So only possibility is that there must be some electric field. Electric field can exert force on a charge which is resting, whose velocity is zero, and that value is q times E vector. So earlier there was no electric field. That means he will conclude, if you observe the things from the frame of reference of the coil, then that observation will be this, that when the magnet is brought closer, near my vicinity the magnetic field is changing. This changing magnetic field produces electric field along the length of the wire in the loop. And this electric field forces the charged particles to move along the length of the wire or along the tangential direction to the loop. So the justification will be this. So changing magnetic field produces electric field along the coil, and this electric field causes the static free charge carriers to move along the wire. And when these free charge carriers move, this results in current that we call as induced current. So he will also observe induced current. He also observes induced current. But what the cause of induced current in one frame of reference is the magnetic field, and in other frame of reference it's the electric field. So what we perceive as two very unrelated things in the beginning, I told electric field and magnetic field are actually two sides of the same coin. If there is some force on a charge due to electric field, according to me, it may be due to magnetic field due to other frame of reference, person in another frame of reference, and due to a third person, it may be a combination of both electric and magnetic field. Let me repeat again. What causes the charge to move is magnetic field in one frame of reference and electric field in other frame of reference, and it can be a combination of both electric and magnetic field in some other frame of reference. So whether the force on the charged particle is due to electric field or it is the magnetic force or electrical force, it is just mere a question of relativity. It is mere a question of point of reference, frame of reference, which frame we are using. So this discussion which we had for case A, that we also refer to as motional EMF. What does it suggest? That whenever a conducting loop or conductor moves in the region of magnetic field, there will be some induced EMF in it, and that's why the name motional EMF. Yeah. So based on motional EMF, we'll do a couple of more discussions. So let's see them quickly. Suppose we have a uniform magnetic field in a region, and direction I have represented using cross. That means it is directed into the plane of both. In this region of uniform magnetic field, there is some metallic frame of wire like so, and in this there is some slider that is also metallic. We assume there is no friction. When this is slider slides over this frame we will assume to be fixed. and it is metallic. This slider is also metallic. They are conductors, good conductors. So it can slide freely, smoothly, without any friction. This point I'll consider as x is equal to 0, and the distance of the slider from the left end, I'll give it the name of variable x. So when we move the slider, x will change, either it will increase or decrease depending upon the direction. So this is suppose our positive direction of motion. This is x is equal to 0, then positive values are there. We are discussing motional EMF, so we have discussed earlier that if there is some conductor which moves in a region of magnetic field, then EMF is induced. But the next question arises, how much EMF will be induced? So we know, students, EMF induced is given by the formula minus Faraday's law, rate of change of magnetic flux. In this in this situation, magnetic field is into the board, velocity of this slider or conducting wire is towards left. So these two vectors are perpendicular to each other. This area, if you see, if I assume the length of this slider to be L, that area will be how much? L times X. And it will vary with time. Why I say vary with time? Because I am moving this slider, so X will change. If X changes, area will change. If area changes, flux will change. Area changes, so A will change, this implies flux will change, and therefore there will be some EMF induced. At this particular location, the magnetic flux phi B will be B dot area vector. Now the magnetic field is directed into the board. Area vector is also in same direction because the plane of this plane of loop is also on the plane of board. So its area vector will be normal to the board. So we write it as B times A. But the area of this loop can be written as X times L. So this becomes BLX. This speed V in one dimension, we can always represent vectors as plus and minus. For example, displacement of plus 2 meter is 2 meters towards right, and minus 2 meters say is 2 meters towards left. So here plus and minus indicate directions. So because our motion is one dimensional, we can write here V as minus dx by dt. Now why did I write minus? Either you can say the velocity is towards left, that is one cause, or in terms of derivatives, if you wish to say, with increase in time, x is decreasing. So this rate has to be negative. We are moving this slider towards this end, towards x is equal to 0 end. So x is decreasing with increasing time. And that's why we have a minus symbol over there. So what we get here, minus d by dt of phi b. Phi b we will replace with blx. And therefore we get minus b is constant, l is constant, dx by dt. This minus we can take it inside. So it becomes minus dx by dt. But minus dx by dt we can put as v. So this is our formula, students, BLV. The induced EMF is given by the formula B times L times B, V, where B is the magnetic field, which I assume to be constant, L is the length of the wire which is moving, and V is velocity with which it moves. One thing I would like to stress over here, that here B, L and V must be mutually perpendicular. I'll discuss this in more detail. Now this derivation can also be arrived at using another analogy, which I'll expect you to do it yourself, but I'll just discuss the qualitative part, not the quantitative part. Imagine these free electrons. These free electrons have velocities, all of them, because this slider is moving towards left, all those free electrons have velocity v in this direction. Magnetic field is into the board. The velocity v is towards left, magnetic field is into the board. So where will be v cross b? V cross b will be like so. The vector v cross b is like so. Thumb is pointing downward. But in this case, uh, because we are having free electrons as charge carriers, which are negatively charged, the force will be upward. So v cross b is downward. That is for positive charge. Electrons are negatively charged, so force will be upward. So here, these free electrons will experience force in upward direction. If I name it as A, B, so force, so Q, V cross B, this force on the electrons will act in the direction from B to A. And therefore, the electrons will move from here to here. And therefore, there will be current in opposite direction like so. So before discussing this, when I was discussing the relativity part, there we have just taken the direction of V cross B. But if you take into consideration the actual flow of charge carriers, it is because of electrons. So that direction will be reversed. What I told towards you will become towards me. What I told towards me will become towards you. But that is just because we have negatively charged negatively charged charge carriers. So there we have assumed Q V cross B, Q we have taken as positive. So even if you reverse that, so there will be some sense of current. So the concept which I wanted to discuss there, different fields in different frames of reference remains the same. Now I'll come to this particular point. I told B, L and V must be perpendicular to each other. Let us consider one situation wherein there is a wire like so. I should not put arrow. It has some length and there is magnetic field in that region. Uh, Say we represent it by cross. Let its length be L. Let the value of magnetic field be B. So here L is perpendicular to B. Magnetic field is directed perpendicular to the length of the conductor. But suppose instead of moving the conductor like so, if we give the velocity in this direction, then the induced EMF will be zero. So don't just bluntly apply this formula BLV. This formula you will apply only if all of these three are perpendicular to each other. If they are not perpendicular, tilted, making an angle of 30 degree, 45 degree or so, then take that component which is perpendicular to the other components. All those three, the components of B, V and L must be perpendicular to each other. Now herein, this particular example, suppose you imagine a charge or a free electron, Q. Its velocity is in this direction. If you try to find force on this particular charged particle, then you see velocity is downward, magnetic field is into the board. So this is V vector and this is B vector. If we apply V cross B, V is downward, magnetic field is into the board. So the fingers will curl into the board. Thumb is pointing in that direction for positive charge. For negative charge, it will point opposite. So force will be in this direction. But do you think the free electrons in this particular wire can move in this direction? They are not allowed to do so. Free electrons are not that free that they can leave the surface of the metal. This is a metallic conductor. So they can move anywhere on the within the metal, but they cannot leave the surface. Because we have a wire, its length is like so. The free electron can move anywhere in this particular direction. We assume the thickness of this wire to be zero, negligible. So the free electron, although the force is in this direction, it cannot come out and therefore it will remain as such. So when there is no flow of electron in this direction, that means there will not be any current. Induced current will be zero and therefore induced EMF will also be zero. Similarly, if we have third case, suppose this is the direction of magnetic field as usual. So I'll end up just by discussing this. And there is a conducting wire straight. So here again length is perpendicular to velocity magnetic field. Now suppose its velocity is also represented by cross. That means suppose this is a conductor, magnetic field is towards the board cross and I take this conductor length perpendicular to the direction of magnetic field, okay? But instead of moving it like this, I move it along the length of the magnetic field, along the direction of the magnetic field. So velocity vector and magnetic field, because they are in same direction, so when you apply Q times V cross B, the force becomes zero. In this case, V cross B becomes zero. And therefore F, which is Q times V cross B, also becomes zero. No magnetic force will act on that particular charged particle, and therefore it will not move along the length of the wire, and hence it will not cause any current induced in this particular wire. So likewise, you can think of, students, if L is parallel to B, what will happen, and the different cases. So neither of among this B, L, and V, no two components or parameters should be parallel. That is the thing. If they are parallel, EMF induced will be zero. If they are not parallel, EMF induced will not be zero. And suppose the magnetic field is suppose in this direction, and velocity of the conducting wire. This is the conducting wire. This is perpendicular. Length is perpendicular to magnetic field. But the conducting wire's velocity, suppose it is in this direction. Then what to do? Here also you should not write E is equal to BLV. B is okay, L is okay. Instead of V, you have to write the component of V which is perpendicular to both B and L. Clear? Actually, in 3 dimensions it should be drawn. The V is not lying in the same plane. V should be tilted like that. So you have to find a component of velocity which is perpendicular to both B as well as L. That component I'm writing as V perpendicular. So here the expression will change from BLV to BLV perpendicular. So I'll stop here, students. So I hope the concepts which I tried to discuss today are clear to you. It will be better if you try to analyze the situation, introspect the situation on your own. That will give you some pleasure, and then you can switch over to solving some numericals. See you in the next class. Till then, take care. Thank you.